All right, dude, we are live. What's up, guys? This is Dem Keys, and today we're going to be doing something a little different. We're going to be exploring a Rust crate called petgraph. I have come across this crate in the past, but I I can't remember exactly when it was. I think maybe it was when I was looking into how to generate graphs using Rust. But at the time, what I was looking for was uh, something with a workflow more similar to, uh, or I guess I should say something more along the lines of dot graph, basically. So the dot language is a graphing language. Basically, you can write down you can describe the entire graph in, using their dot syntax, and then you can use one of the GraphViz tools. I think that's also called Dot. I don't remember. But yeah, you can use one of the GraphViz tools to convert that text representation into a rendered image. So the tool is going to actually, draw out the entire graph for you based on what you have described. So at the time, I was looking for something more along those lines, and I did come across petgraph at the time, but I wasn't looking for exactly petgraph at the time, and so I didn't really see too much potential in it. I knew that it's capable of doing a bunch of very important things surrounding graphs, but at the time, specifically what I was looking for, it was only kind of able to do it because you can describe a graph in petgraph and then export that to the dot format, and then I'm guessing you would then feed that into, the GraphViz tool and produce your rendered image, right? Um, I I don't remember exactly why I didn't go forward with it. I think I decided to um, learn the dot language itself, and well, uh, I've only kind of learned the dot language. I learned very basic stuff. I didn't go into advanced concepts like I think they have the concept of subgraphs as well. I never actually went into that. And at this point, I don't think I will because it clicked to me yesterday when I was looking into petgraph. I was like, okay, oh, you know what? Another possible reason why I didn't go too deep into petgraph at the time when I discovered it, not yesterday, but like a while back when I discovered it, which must have been like a couple months. I don't remember at this point. Um, yeah, I don't remember at this point, but it I think maybe I even explored it. I think even words. I think I even explored it on stream. Maybe I'm not sure, but I did explore it at some point. Whether it was on stream or not, I don't remember. But I did explore it, and I think another reason why I decided not to go with it was actually there might have been multiple reasons. I'm trying to find like one reason why I didn't go with it, as if there was something wrong with it. There's definitely nothing wrong with it. It's just that based on the workflow, it seemed more convenient to me to just learn how to create dot graphs and then feed that into the GraphViz tool. I don't think I was very deep into my Rust journey either at the time. Like I knew basic Rust, very very basic Rust. There was still a lot of components of it that I didn't know. There's still a lot of different features of it that I hadn't yet explored, and so I don't know. Maybe the syntax looked a little daunting to me. I'm not sure exactly what all my reasons were for not exploring it. Why am I making up excuses? Anyways, I discovered petgraph a while back. I didn't go with it at the time. Now I'm a lot more comfortable with Rust, and just yesterday I came across petgraph again, and this time it was for a different purpose because I was looking into graph generation stuff in Rust, and then I came across petgraph. And what petgraph does, keeping aside the rendering, because it doesn't necessarily handle the rendering. Well, okay, maybe it. I don't know. Maybe it does because I know that it outputs the dot format of your. It can output your graph that you have described in Rust. It can output that in the dot format, but it's going to give you dot code. So you have to then feed that into the GraphViz utility and generate the thing using that. I don't know if they have like helper functions for that or something in petgraph. I'm going to have to check. Um, However, the important thing with petgraph is that it it focuses on the idea of graph structures, graph data structures themselves, not the rendering of the structure, but the graph structure itself, different types of graphs, different types of operations that you can perform on graphs, different ways to traverse, uh, different ways to traverse the graphs, and so on. And this made me come back to a thought that I'd had a while back, which is that I don't really understand graphs all that well. Let me explain. So, in the past, I knew about only like two types of graphs. Just a second. Actually, let me hydrate. Before I started the stream, I remembered that I did not hydrate. So let me hydrate and then I'll uh, continue. Okay, and let me also just open up my stream in on my phone so I can see the chat. Okay, so what was I saying? I was saying, yeah, I a while back I realized that I don't really understand the concept of graphs. Like, okay, so I knew about two types of graphs. Okay, one is the our plotting stuff where we create plots or charts or those kinds of graphs to represent data points. And then the other kind of graph was node-based graphs where stuff like Unity's shader graph, Unity's VFX graph, the Blender shader. I forgot what that thing is called, but the Blender node-based shader editor. Um, that's also a graph in a way. And then you have the Blender geometry nodes. That's also a graph. Now here's the thing, right? I've seen the term graph being mentioned before in multiple different other scenarios where it was being talked about in a way that didn't necessarily have a visual representation. And at the time, it just never clicked to me. Like the concept of graphs, it just never clicked that, oh, this is a structure that represents some kind of data, and then you can traverse this graph to create some sort of functionality. You get what I'm saying? Like it that those dots didn't click because I'd never done research on graph related stuff. And each time I come back to these concepts, I realize that okay, we have the concept of a graph and there is something being defined in this graph, and there can be like a there can be a rendered version of it to show you what exactly the visual representation of it looks like. But I don't fully understand the concept of graphs. So I wanted to do research on that. And so I decided to ask Gemini some questions regarding this. So I'm just going to read out what Gemini had said. Also, for now, we can have this thing open here. Okay, so um, sorry, zoned out. Okay, so here's what I asked Gemini. I said that, hey, so I'm learning how to use the pet graph crate, and this is making me realize that I guess I don't really even understand graphs. Let me explain. And then I explained the whole thing that, I knew about Unity and Blender and like those kinds of graphs. And I only kind of understood what was going on there. I knew that, okay, they're using the concept of a graph to represent some kind of functionality. And then whatever that graph is, it is being presented. Like it is being shown. We are seeing a visual representation of it through these node based editors and stuff. So I kind of understand it, but I feel like I don't fully understand the the back end of graphs. I also mentioned that in the past I'd looked into, or well, in the past, what I knew about in terms of graphs was the plotting or the plots and charts and those kinds of graphs versus these graph data structures, right? So I wanna get a better understanding of graphs themselves. Um, And then finally, I asked two questions. I think I can read those out. Yeah. So I said, okay, this made me realize that one, have been thinking of graphs in the wrong way, or rather, only been looking at the final rendering of the graph as opposed to the data structure representing the graph. And because, dude, this concept has come up in Unity multiple times. Not just with shader graph and VFX graph. There were also other concepts. Like they had the DSP graph, they had the playable graph, they had a bunch of different like graph APIs, and I never truly understood the concept there. So I feel like learning about graphs here would be incredibly helpful for me because I would be able to make some. I personally feel like I would be able to make something complex with graphs, and who knows, maybe I might be able to use this in game development as well. Okay, so one, okay, let me restart that because I'd said two things that I'd realized. So this is making me realize that I one have been thinking of graphs the wrong way, or rather, only been looking at the final rendering of the graph, as opposed to the data structure represented by the graph. And two, I don't really understand or know anything about graphs to begin building any such systems. Give me a second. Okay, then I said, but I want to learn all about graphs, how they work, and how they can be used to build such interesting things. So far, what I know is that they're these data structures. You can build the structure and then traverse it using various algorithms, but that's about all my understanding, and even that's kind of a limited understanding. Okay, so then Gemini replied saying, it's a classical quote unquote name collision in computer science that trips up almost everyone. You aren't thinking about them the wrong way. You're just moving from data visualization, which is charts and plots, to discrete mathematics, which is graph theory. Think of it this way: a plot is how you look at the data, but a graph is how you connect the data. Okay. The anatomy, vertices and edges. Okay, cool. At its simplest level, a graph is just a collection of two things: nodes, which are vertices. These are the points or entities, example, a person, a city, or a math operation, and edges, which are the lines or relationships connecting those points. When you look at Blender's when you look at Blender or Unity's shader graph, each box, quote unquote, is a node, and the wires you pull between them are edges. The data structure is just a list of node. The data structure is just a list of these nodes and a list of which ones are tethered together. All right. Common flavors of graphs. Graphs aren't one size fits all. Depending on what you're building, you'll choose a specific type. You have undirected, directed, weighted, cyclic, and acyclic graph. Is that cyclic or cyclic? I'm going to say cyclic. Okay, whatever. And they've given like definitions, they've given descriptions for each type. And then Gemini goes on to say DAG, which is directed acyclic graph. Um, Gemini is describing why DAG matters to me. So you mentioned Blender and Unity. These systems almost always use directed acyclic graphs. Directed means data flows from an input node to an output node, and acyclic means you could plug the output if you could plug the output of a color node back into its own input, you'd create an infinite loop that would crash the renderer. The system prevents cycles to ensure the math actually finishes. Okay, all right. I should keep that in mind. Okay, then, how the computer sees it. You mentioned that petgraph is a bit confusing because you're looking at the logic under the hood. Computers generally store graphs in two ways. One is an adjacency list, and the other is an adjacency matrix. An adjacency list, each node keeps a list of its neighbors. This is memory efficient and very common. Adjacency matrix is a big grid or a 2D array where 1 means connected and 0 means not connected. This is fast for looking up specific relationships, but uses a lot of memory. Okay, why use a graph? The quote unquote power part. Once you have your data in a graph, you can run algorithms to answer questions that would be impossible with a simple list or array. Traversal, BFS and DFS. Traversal, visit every node in this shader to make sure they are all compiled. Then shortest path, what is the fastest way for this data to get from point A to point B? Then topological sort, in what order do I need to calculate these nodes so that every node has its inputs ready before it runs? This is exactly how Comfy UI or Blender knows which node to process first. Okay, moving forward, don't let the abstraction of petgraph scare you. Actually, okay, I don't know if I gave that impression that petgraph, maybe I did, and I think it's because petgraph did actually initially there was like a lot of information that I wasn't necessarily going to be using at the time. To be clear, at the time, I felt like I wasn't going to be using, and I didn't fully really even understand that what this is doing is this is a very powerful library that gives you the ability to build these different types of graphs and also traverse these graphs in different ways. And additionally, it gives you the option to output the graph that you have made to the dot format. So one of the things that I was trying to do back then, it could have actually been accomplished using petgraph, but I purposely chose to go with the dot thing just so I can learn. And it was a good learning experience, to be fair. I didn't finish learning it all the way. And once I go deeper into petgraph, I'm going to be honest, I don't think I'm going to go deeper into the dot syntax. Once I go deeper into petgraph, then I don't think I'm going to be going deeper into the dot syntax because I won't have very many reasons to do that. Because I can just use this crate, build the entire graph, and then export it to the dot format using, you know, using petgraph itself. And additionally, this allows me to focus on building the graph data structure within Rust code and then exporting it to this format if I need to. I feel like that's a little more powerful than just knowing how to write out the dot syntax. I mean, the dot syntax can have its own, benefits, but for my purpose and considering my environment where I pretty much always have an IDE available, I pretty much always have the ability to open up a Rust project if I need to. Considering all that, I think going with petgraph is a good idea. Not only that, I feel like learning about graph theory is going to benefit me in more ways than one. Because I already mentioned the thing about, hold on, words. I'm going too fast. Because I already mentioned the thing about doing graph related stuff in game dev. But additionally, I feel like I would be able to use graph related stuff in various other situations as well. One bonus here, by the way, okay, so this is probably another thing that was added as like a huge plus point for me. Um, where was it? Create features. So it mentions here STD. This is one of the features. By default, these features are enabled and STD is enabled by default. This enables the Rust standard library. Disabling the STD feature makes it possible to use petgraph in no STD contexts. That is exciting for me because this means that I can use graphs if I need to in, um, what do you call it? In embedded Rust. So when I'm doing ESP32 Rust programming, if I ever need to create complex logic, I would be able to do it using graphs. Okay, so where do we go from here? I need to. Oh yeah, there's the moving forward section. Don't let the abstract pet graph scare you. It's essentially just a very organized bucket of your quote unquote boxes and wires that provides you with the math tools to walk through them. Since you're looking at pet graph specifically, would you like me to show you a simple code snippet of how to define a basic directed graph and add a few nodes and edges? No, hold on. Actually, I would like to explore the concept of graphs more in detail. I can look into how to create those graphs in petgraph later based on its documentation. For now, I would like to further explore and understand graphs the various types, how I'm meant to be using them, and the concept of algos in them, algos as in algorithms in them. Yeah, because like petgraph, the idea with petgraph is that like it gives you the ability to create these various different types of graphs. It also gives you a list of algorithms that allow you to traverse the graph. So, okay, based on what this says here, petgraph is a graph structure library. Graphs are collections of nodes and edges between nodes. Petgraph provides several graph types, each differing in the trade-offs taken in their internal representation. So, okay, wait. Petgraph provides several graph types, algorithms on those graphs, and functionality to output graphs in GraphViz format. Both nodes and edges can have arbitrary associated data, and edges may be either directed or undirected. So I'm glad that I explored a bit of the dot syntax before this, as in not recently, but like in the past, I have explored a bit of the dot syntax. So now I know that, okay, an undirected graph is something that just connects, one node to another and another to another, and like it just connects nodes together. You don't necessarily have a sense of direction of the connection. So it's not like one node is connected to, it's not like node A is connected to node B. So it's not like there's, you know, a direction of the communication. It's just that node A and node B are connected together. So the connection can happen in whatever way you want. So if there is a direction there, showing that, the connection is going from node A to node B, that's a directed graph. And if there's no direction specified within these edges, then it's usually an undirected graph. I need to look into if there is the concept of like hybrid hybrid graphs where you have both directed and undirected connections. Though I'd imagine that would get a little bit that would make graph traversal a little bit complicated, because like then you would also have to keep in mind that you know so and so edge is directed, so and so edge is undirected, and like that kind of complicates things. Anyways, okay. Here's Gemini's response. This is a great mindset to have. Before diving into code, you need a mental model of how to think in graphs. In computer science, a graph is basically data plus its relationships. Here's a deeper dive into the architecture, types, and logic of graphs. Okay, defining the connections. Should I open up a new conversation in Gemini CLI? No, I feel like in this way I'll have better quality information. If I'm doing it through Gemini Web, I feel like I'll get better quality information. If I'm doing it through Gemini CLI, then I would need to do it using Gemini Pro or Gemini 2.5 Pro. Oh, also here it's using Gemini 3, so that's also something. Um, I need to see if there's a way to export the data of the output. So like I asked the question in AI Studio, in Google's AI Studio to Gemini, and then um, I give it the explicit instruction to give me the output as either JSON or Markdown. Well, I think JSON is better. Yeah, I think JSON is better for that specific purpose. I think JSON is, well, no. I think Markdown would be better for that purpose. because then I could just copy that entire markdown and then paste it, and then I have the thing there. Um, Let me give that a try. Hold on. I'm gonna test something out here. Okay, this is Flash Preview. I'm not looking for Flash Preview. There's Flash Preview, there's Pro, there's 2.5 Pro, which is free. Um, Wait, system instruction template. Wait, I'm able to specify the output here, right? I think I remember something about being able to specify the output that it gives me. There was something I haven't touched Gemini. I haven't touched Google AI Studio in a while, so I can't remember all of the like settings and stuff that they had. But they did have like settings for where are those settings gone, dude? Oh, they have system instructions. You will always do so and so, so and so, so and so. Okay, avoid using gradients. Oh, Drawn Blood. Hello, hello. Welcome to the stream, and thank you for the hydration reminder. Yes, yes, thank you for reminding me. We are half an hour into the stream, and I need to hydrate. So give me a second here. Hey, Drawn, how's it going? So we are today learning about um, we are learning about graph data structures, and I'm trying to understand, I guess, graph theory itself. So I wanted to be able to show some of the output from Gemini in a markdown form. Okay, so I can create a prompt. Wait, always give output in markdown. Okay, so let's save the change here, and we're going to use Gemini 2.5. Okay. Hi, hi. We'll be doing some assignments in a bit. Drawing ribs. How's things going here? I got ads. Yay, I hear them keys again. Welcome back. Welcome back from the ads. Also, awesome. Hell yeah, you're gonna be doing some drawing. Uh, Things are good. I'm excited to go into or dive deeper into this concept of graphs because I've never actually had the chance to explore the concept of graph structures, like where you can define a structure that is conceptually a graph, and then you can traverse that graph to do something useful with it, right? That whole system, that's still kind of new to me. And in the past, I've used plenty of systems that were built on that concept. So if you look at something like Blender's shader nodes, I believe Blender's geometry nodes as well, and in Unity you have shader graph, you have VFX graph, you have various other like node-based editors. A bunch of them they implement the concept of the words. They implement the concept of graphs, and I've never truly understood how these things work on a lower level. So I'm trying to get an understanding of that. And then we're going to be using this crate in Rust called petgraph to first create the graph. I don't know how much of this is going to happen in today's stream because I only stream for like an hour and a half to maybe 2 hours. And a lot of that time, I end up spending like being distracted with various different topics. So I don't know how much of it is gonna happen today, but okay. So I'm gonna get Gemini to generate this sort of well, okay, dude. If I'm doing that, and if I'm doing it through Gemini Pro here, I might as well just open up Gemini CLI, a new instance of Gemini CLI. What was I doing here? What is this conversation? Holy shit! This is wait. What is this from? Yo, okay, look at the in the top right. I don't know if the top right is visible. Everything coming out of your mouth so smart. I do scribbles and call it a day. No, I mean your thing is like super creative, right? There's a bunch of smarts that goes into what you do as well. I hope the drawing session goes well, by the way. Um, but yeah, yeah. What was I? Hold on. If you look in the top right, are you able to see? No, the top right of the specific window that I'm trying to show you guys is it's hidden, but it has reached the buffer has reached 49,187. I I don't remember what the limit is. Oh, no. Okay, so yeah, I should have been specific about that. So I'm talking about the window that's in the bottom left. I'm talking about the top right of that window. And that, yes, that is covered up. Um, I could temporarily show, let me go into this and come here and we can temporarily hide this one. So if you look in the top right of that window, there's a number or there's a range that says 126 by 49,000, or well, now it's 0 by 49,000. 49,000 is like how far up it is. Like if you look at how much I'm scrolling here, this is how long this entire course, quote unquote course, has been. And holy shit, we've been learning so much. We've been learning so much. It is crazy. I love when we have to make collages on our stream. That is this shows like how long this conversation has been going, how far up the let me see here if I can catch one of the topics. So this topic is for vectors. I don't remember which chapter that was. Let's scroll up more and see if there's trait bounds. Back up. How does trait bounds come before vectors? No. Trait bounds is in traits. I don't remember how vectors came in. Maybe vectors was part of something else that was being taught, because there's traits here. There's trait bounds. I don't remember where I happened to see vector. Yeah, yes, totally. I've learned so much. Okay, this is in my case. This is like a huge. Wait, hold on. If I do this and oh, now I feel silly. The reason it was 49,000, now it's gone down to like 2,000 something. Okay. I have another group thing due in less than an hour, I realized. Have fun and happy learning. Drawn, thank you very much for stopping by. Have fun with your thing, and good luck with the drawing as well. I appreciate you stopping by and chatting. Let me bring this thing back. Yeah, now I feel kind of silly because I thought it was like 49,000 something lines. I believe this is, I don't remember if it's lines or characters. Um, this is lines. Okay, it's lines. I thought it's 49,000 lines, but in reality, the thing was just kind of broken up. And so, like, sometimes the formatting gets kind of, it gets kind of messed up and it becomes, um, how do I explain this? So, like, what you are seeing here, for example, um, you see like this entire this entire paragraph. This thing, it could be broken up into multiple lines due to some sort of formatting error, and all I have to do is just exit this. I forgot what this mode is called, copy mode or scroll buffer mode, and it fixes itself, and then I can scroll back up there. So it's not 49,000 lines. It was like 2,400 something lines. Anyways, let's open up a new conversation. Wait, that's crazy. Holy shit. Give me a second, dude. Give me a second, dude. It started raining like heavy. I'm gonna get up for like a couple of seconds and go take a look. It started raining like heavy. Hold on. Wait, I just realized if it starts raining right now, then I'm probably also gonna have like random internet issues. You know what? Never mind. It slowed down. It was it was heavy for literally just a few seconds. Okay, anyways, carrying on. I think we can start a new Gemini conversation somewhere here. Let's see which of these is free. Nested progress bars. What was this? Oh, this was to do with the TQDM. Yeah, yeah, this was to do with TQDM. Okay, I should keep in mind that TQDM is a thing, just for future purposes. That being said, for now, I think I can quit this and uh, just reopen Gemini here. Just a second. I need to make sure that we are not losing internet. No, we are good. Okay, so let's open up Gemini again here and wait for it to open up. And in the meantime, what was I talking about? Yeah, I think I was gonna. So how should I frame this prompt? I can, okay, while this is opening up, we can probably open up NeoVim here. The copy thing is not gonna, it's not gonna happen properly if I do it through tmux over SSH. Um, so I guess I'll type it out here and just, read it out loud as I'm typing. I don't know if you guys can hear the thunder right now. There's like a rumbling kind of thing going on. Okay, so um, what was I? Yeah, um, I want to learn about graph data structures and the concept, no, graph data structures, well, graphs in general, graph data structures. No, how do I preface this? Because like in that other conversation, there was already a bunch of there was already a bunch of like, you know, um, there was already a bunch of context there, so I didn't need to go too deep into that. Okay, I want to learn about no. Okay, I've been exploring the pet graph crate. So this will tell Gemini what type of graphs I'm trying to go for. I've been exploring the pet graph crate in Rust, and this made me realize that I don't really understand the concept of graphs, um, the various types of graphs, um, how they are meant to be used, how they work, what algorithms I can run on them, and so on. I would like for you to teach me um, all of this so that I know something about graphs and can build things with or build systems using graphs. We don't have to go into the the coding part. I'll look at the the pet graph docs for that. But first, I would like to understand um, the theory portion of graphs. And as always, I think I also need to mention that um, no right actions necessary. Um, just give me the info. So I'm going to copy this and drop it in here. Oh, where is it? Um, Wait, did I not open up? No, I'm pretty sure I opened up a new Gemini instance. It was somewhere here. Where did it go? Oh, there it is. Okay. So, paste. Right. I've been exploring the pet graph crate in Rust, and this made me realize so and so, so and so, so and so. Okay. Oh God, is it gonna ask for the authentication thing again? Because I haven't done any new prompts on Gemini CLI in a couple of days. I do have the instances still open. No, I think we're good. I don't think it's gonna ask for um, authentication again. I did have this issue of authentication on one of my other machines, which is actually the machine from which I'm um, SSH'd into another machine right now. I don't know. I'm not gonna explain it very well, but I had like an authentication issue with it for some reason. Um, so there are multiple ways that you can authenticate with Gemini, with the Gemini API, and one of the ways was when you try to launch Gemini CLI, then it's gonna give you a link, but it's also gonna automatically open up that link in your browser, so you can then allow Gemini API or allow Google AI Studio. I don't remember which specific platform it is. It's something Google related itself. It's something specifically Gemini related that you're allowing to access your account. Basically, it's just it's using your account for authentication, because you have to give some kind of authentication. So that's one way to authenticate, right? Another is you just get the API key. You generate an API key within AI Studio, and then you save that somewhere on your machine and have Gemini CLI read that all the time. Initially, I didn't want to do that because this way was working. The way that it opens up a new page, and then you allow your account, you authorize the access basically. But then some kind of bug happened, because of which it went into this loop where each time I would launch a new Gemini CLI instance, it would ask me to authenticate again. And after this happened a couple of times, I looked it up online, and a couple of other people were having this issue as well. And finally, I was like, okay, let me just give the API key thing a try, because if I don't get this to work, then Gemini CLI on my machine is completely useless. So I did that, and then after that, it's working. Well, after that, it doesn't keep bugging me for authentication. The interesting thing is, the interesting thing is, on that machine, I had the authentication issue. On this machine, like the machine on which this tmux server is running, the machine on which, let's say, this Gemini CLI session is currently running, on this machine I had a weird issue where one day, all of a sudden, out of nowhere, Gemini was just not found. Gemini CLI was just not found. I don't remember what the thing was that broke it. I think I still have the because I then had to go and have a conversation with Gemini Web to diagnose this issue. And after after a while of trying a bunch of different things, which I'm glad that I spoke to Gemini Web about this, because I would have no way of, well, I would have a way, but it would have been really, really hectic to, go and check all of the different paths where npm stores, various things. Uh, Gemini Web knew all of this stuff and gave me all of the information in one location. It was like, okay, check this, go and do that, test that, and this and this. I did all of that, and I returned back with whatever the output was, and then Gemini would be like, okay, so based on this, we know that this is a problem. So now you have to try this and this and this. Then I would go and do that, come and give the output back to Gemini Web, and then again, eventually we got down to what the issue was, and I fixed the issue. I don't remember exactly what the issue was. I'm pretty sure I mentioned it on stream later on. Actually, I don't remember if I streamed that day, because that specific day I was late to the stream, or I maybe didn't stream. I don't remember. It was one of the two. Um, I was either late to the stream or I didn't stream, and the reason was because Gemini CLI, just out of nowhere, it was not found on the machine. So, like, entering Gemini would just not work anymore for some reason. Anyways, so we have our information here. Okay, so what are we looking at? Of course, it's a great idea to understand the theory of graphs before diving deep into a specific library. Graphs are one of the most fundamental and versatile data structures in computer science. Let's break it down. What is a graph? The core concept. At its simplest, a graph is a way to represent relationships between objects. The objects are called nodes or vertices. The relationships are called edges or links. That's it. Think of a social network. Each person is a node, and if two people are friends, there is an edge connecting them. There's an edge connecting them. Or think of a map. Each city is a node, and roads between them are edges. Then, key terminology. To talk about graphs, you need to know a few basic terms. Vertex slash node is an individual entity in the graph. Example, a person, a city, or a web page. Then edge or link is a connection between two vertices. Example, a friendship, a road, a hyperlink. Neighbor or adjacent. Two vertices are neighbors if they are connected by an edge. Degree for undirected graphs. The number of edges connected to a vertex. A person with 500 friends has a degree of 500. I didn't know that. Okay. In degree, out degree. In degree, the number of edges pointing to a vertex. Example, how many people follow you on Twitter? And then out degree, the number of edges pointing away from a vertex. Example, how many people you follow. Then path, a sequence of vertices connected by edges. A path from city A to city D might be going from A to B to C to D. Okay. Then cycle, a path that starts and ends at the same vertex. Okay, so A to B to C back to A. And then weight, a value assigned to an edge representing a cost, distance, or capacity. What? A value assigned to an edge representing a cost, distance, or capacity. Instantly, when I saw weight, instantly my mind went to, hey, isn't this how a feed forward neural network gets represented? The interesting thing is there's a computational graph being generated there. So even there's a concept of graphs. Like, this is crazy, dude. I've, by not learning about this concept, I've been missing out on so much in the past. But I guess, as time goes by, whenever I'm ready, usually this is what happens with me. I'll come across a concept because it's not like I haven't explored graph related stuff before. This graph theory, I've looked into it before. I well, at the very least, read stuff up on Wikipedia about this, and at the time, I wasn't grasping too much. I was grasping somewhat, but then I don't know what it was. I just wasn't really very. I wasn't very attached to the topic, and so I didn't really go too deep into it. But then now, as time has gone by, now is the right time for me to get into this, and so now I actually have interest in it. So now I'm going deeper into this concept, and thanks to crates like petgraph, it's going to become super easy. I'm hoping it's going to become super easy for me to define these graphs and also traverse these graphs. So um, I'm not going to have to work on the implementation detail. I'm going to be able to actually build something with it. There's a specific terminology for this. Um, I guess I can say I'm not going to have to worry about the low level implementation of it. I only have to worry about how I'm going to be using it. Because previously I would also have to worry about how those tools would be implemented first, because that's what happens when you try and learn stuff from, like, when you try and learn these things off of Wikipedia, it won't be immediately mentioned to you, or you would have to, like, read for a while before it's mentioned that, oh yeah, there might be libraries that implement this. And also in the past, I didn't always immediately, think that, hey, let me check if there's a library that does this. A lot of times my mind would go towards, hey, I might need to implement this myself. And that's not necessarily a bad thing because that has led to me learning a bunch of things, but then it's also bad in the sense that I don't immediately think to check if there's already a library that does this. Because if I did do that, then I would be able to get started with the concept itself. I would be able to get started with actually using the concept rather than implementing the concept first and then using the concept. Because implementing it and then using it, it can teach you a lot, but it also takes a lot of time because you have to, learn how to implement the thing. It's kind of like, um, it's kind of like implementing a neural network from scratch and also implementing the training mechanism from scratch before you can actually build and train a neural network. Like these are two very different things at this point in time. You don't necessarily have to learn how to implement the whole thing from scratch because you have frameworks like PyTorch that that do a significant amount of the work for you. Give me a second. I just remembered that this thing has crashed on another machine. I mean, but dude, I'm excited. Like, I'm trying to imagine the various graph related things that I would be able to implement because I can mix NLP and graph related stuff. Yesterday I was having an extensive conversation with Gemini about how I would be implementing this idea that I had for my little, you know, um, I need to think of a name for it, but it was this thing that I wanted to implement that's going to help me trace back all of my conversations without having to read through all of the sentences. It's going to help create a mind map of the various topics that I branched out to as well. And anytime I feel stuck, I can just pause and go take a look at that graph because it's going to be constantly generating the mind map, right? So I can then pause, go take a look at the graph, and then once I know what I'm uh, talking about, I can then continue from there. This actually reminded me I need to add in functionality into that graph, into that tool, to be able to continue or create a new branch from where we left off. So let's say I'm talking about topic A, that spawns a thought about topic B, and then I keep talking about topic B, but then I remember that, oh, hey, I was talking about topic A. So whenever this happens, the program should traverse the graph and find where the topic is that I remembered about, and then I need to jump. The program needs to create a new branch from that point, not from where it currently is. That's something I need to be careful of, and I'm definitely going to need this. I'm definitely going to need petgraph. I'm glad that I'm exploring petgraph because otherwise I would have been implementing all of this graphing functionality from scratch, and that would be a nightmare because it's not just the concept of the graph itself, it's also algorithms for traversing the graph. Okay, anyways, let's continue. So, path, cycle, weight. Weights are, I believe, assigned to edges. Yes. Okay. A value assigned to an edge, representing a cost, a distance, or capacity. On a map, the weight of an edge or road could be its length in miles. Interesting. Okay. Yes, actually, I didn't think about that. That is interesting because you could then represent something like that using a small graph, but then, so, okay, you could have three different edges, right? Showing three different paths. They all will have the same length. Like visually, they would all three look the same. They won't look longer than the other, but then they can represent different distances. So you can just add the number there. So that's the weight of the edge. That is super interesting, dude. Okay, then types of graphs. Graphs are categorized based on the properties of their edges. Undirected versus directed graphs. Undirected. Edges have no direction. If A is connected to B, this is what I was talking about earlier. Um, I don't think I need to read this because I already know graph versus digraph. So undirected graph versus directed graph. Thanks to thanks to the dot graph syntax, by the way. Anyways, I can read this. Edges have no direction. If A is connected to B, B is also connected to A. This is like a Facebook friendship. It's a two-way relationship. Then you have directed graph. Edges have a direction. A, no, an edge from A to B doesn't imply an edge from B to A. This is like Twitter, where you can follow someone without them following you back. Okay. Unweighted versus weighted graphs. Unweighted. Edges simply represent a connection. The question is, are A and B connected? Wait, unweighted versus weighted graphs. Unweighted, edges simply represent a connection. The question is, are A and B connected? All connections are equal. Okay, so with an unweighted graph, all connections are equal. With a weighted graph, each edge has a numerical weight. The question is, what is the cost to go from A to B? This is essential for problems like the shortest route in a GPS. Okay. Cyclic versus acyclic graphs. Cyclic. The graph contains at least one cycle. You can follow a path and end up back where you started without retracting your steps. Most social networks are cyclic. Acyclic, the graph has no cycles. Um, Wait, hold on. Back where you started without retracing. Did I say retracting your steps? No, without retracing your steps. Most social networks are cyclic, sorry. Then acyclic, the graph has no cycles. This is very important for representing dependencies. A directed oh, um, a directed acyclic graph is a crucial type of graph. Think of a task list where some tasks must be completed before others. You can't have a circular dependency. Task A needs B, B needs C, and C needs A. So it must be a DAG, directed acyclic graph. I didn't think about this. I didn't think about how that concept of uh, tasks having like their own dependencies and stuff. Because like I've seen that with Task Warrior. I've also seen that with a couple of other task management utilities. It never occurred to me that this could be one of the things. So like we could set up a graph for this as well. I need to see how fast it is to traverse these data structures. I'd assume there's definitely optimizations in place to um, to speed up the traversal of this. So even if I did multiple traversals, it would still end up being fast. But then that depends on how big the graph is, right? I need to see how to actually. We could also look into if there's a way, because I believe Rayon is supported in petgraph, and I think that might be for traversal. Give me a second. Let me check here because I do remember Rayon being mentioned. Rayon is for parallelism, data parallelism. So if you have like computational operations that you want to parallelize, then you would use something like Rayon. Where was it? I think it was here. Under where are those? Yeah, here. Enable parallel iterators for the underlying data in graph map requires Rust version as required by Rayon. Okay, okay. All right. Um, Let me get back to this. Okay, so how graphs are represented in code, how they work. There are three common ways to store a graph's structure in memory. Your choice affects performance and memory usage. So there's adjacency list, adjacency matrix, and edge list. Adjacency list, what it is, a collection like a hash map or an array where each vertex has a list of its neighbors. For a weighted graph, the list would store pairs of neighbor weight. Example, for a graph where A is connected to B and C, the entry for A would be A, B, C. Okay, all right. Oh, okay, all right, okay, okay. I'm kind of getting it. I'm trying to follow this. This would obviously depend on like the type of graph, right? Um, and it would also depend on um, the implementation that's done within the library that's implementing this. So they might have their own way of implementing something like this, and I guess we'll find out once we explore. But yeah, um, this is best for most real world scenarios, especially when the graph is sparse, has many nodes that has many nodes but relatively few edges. It's efficient for finding all the neighbors of a given node. Then adjacency matrix, what it is, a 2D grid, a matrix where so and so is one, or the edge weight. If there's an edge from vertex I to j, and zero otherwise. So this represents the connections. Yeah, this represents the connections, and then you specify if it's a 1 if they're meant to be connected, and 0 if they're not meant to be connected. Example, a 3-node graph, A, B, and C, would have a 3 by 3 matrix. If A is connected to B, the cell at row A, column B would be 1. Okay, hold on. It's a 3 by 3 matrix for A, B, and C. Oh, it's a 2D matrix. I need to keep that in mind. It's a 2D matrix. Yes, yes, it's a 2D matrix, and we are representing connections between this. This is reminding me of what was it called? Collision matrix. It was called the collision matrix in Unity. I remember I'd done a tutorial on this. It's basically where you could set up different layers to have collision with each other. So this way you could define custom collision behavior, and that's really powerful because that allows you to add in like a lot of customizability, at least up to where the layers are allowed. I don't remember exactly what it was based on. Was it based on the concept of layers or tags or something else? Because I haven't touched Unity in a while, but there was a thing where you could they had like a I can show it. Give me a second. Let me just switch to BRB. I don't know how much it has changed over time, but it's like a core Unity concept. Unity collision matrix. Just a second. Well, I mean, yeah, this is enough, right? I can show it through this. Layer-based collision. Let's open this up. And I just need to show an image of the collision matrix. It's a pretty small image, but you'll be able to see it. Okay. So this is the collision matrix. And here you have a couple of different layers, and you can then select which layer collides with the other layer. So this way you can define like custom collision behavior. Oh, wait, I didn't transition back. No, I did transition back. Okay. Yeah. So this way you can define custom collision behavior. Okay. Now back to this. So adjacency matrix. Right. This is best for dense graphs where most nodes are connected to most other nodes. It provides a very fast check to see if an edge exists between any two specific nodes, but can use a lot of memory for larger sparse graphs. Then you have edge list. What it is, a simple list of all the edges in the graph. Each item in the list is a pair or triplet for weighted graphs representing a single edge. Example, this. Okay, so this is just a list of the edges. It tells you this is connected to that, that is connected to that. Okay, best for simple storage or when you primarily need to iterate over all edges. It's not efficient for finding a node's neighbors. Then, common graph algorithms and their uses. This is where graphs become powerful. Here are the main categories of problems you can solve. Traversal slash searching. How do I explore this graph? Breadth first search, and then there's depth first search. Okay, breadth first, BFS. This explores the graph layer by layer. It starts at a node, visits all its direct neighbors, then visits all their direct neighbors, and so on. Use case, finding the shortest path for an unweighted graph. Example, what's the minimum number of connections between you and a celebrity on a social network? Okay. Then depth first search or DFS. This explores as far as possible down one path before backtracking. It starts at a node, picks a neighbor, and explores that neighbor's path to the very end before returning to explore other neighbors. Okay. Use case, detecting cycles in a graph, solving mazes, or words. Topological sorting. Okay. That's interesting. I never thought about using graphs to solve mazes. That should be something interesting to implement. Actually, that should be something interesting to implement. Okay. Then, shortest path. What is the cheapest slash fastest way to get from A to B? Uh, I'm I don't know how to pronounce that. I'm just gonna say Stra's algorithm. No, how do you say that? Dijkstra's. I think there might be like silent. This is probably not English, so I need to learn how. It could be Dijkstra's. I'm just going to say Stra's. Stra's algorithm. The classic algorithm for finding the shortest path from a single source node to all other nodes in a weighted graph with no negative weights. This is the foundation of how Google Maps finds driving directions. All right. Then A star search. I remember this because this is a pathfinding algorithm. A star, a smarter version of Stra's. It uses a heuristic, an educated guess, to prioritize paths that seem to be heading in the right direction. It's widely used in video games for character pathfinding. Then Bellman-Ford algorithm. Slower than Stra's, but it can handle graphs with negative edge weights, which Stra's cannot. Then topological sort. In what order should I do these dependent tasks? What it is, a linear ordering of nodes in a directed acyclic graph such that for every directed edge, wait, such that for every directed edge from node A to B, wait, back up. a linear ordering of nodes in a directed acyclic graph such that for every directed edge from node A to B, node A comes before B in the ordering. Use case, a project builds system. You must compile dependencies before the main program. Wait, there's graphs used in this as well. That's crazy. Holy shit, we are discovering so well, okay, I don't know if that's the case for sure, but I mean that does get used a lot in especially in something like parsers, for example. um, Compilers, they, the one of the steps in compilation is also the parsing of the text, and there's like a whole bunch of things that happen there before before it actually gets compiled, right? There's a whole bunch of like syntax checking and all that going on, and a lot of your code, in fact all of your code, it gets compiled into like a tree type of structure. There's much more, sophisticated algorithms, and there's a whole the system is much more sophisticated than what I'm saying, because compiler tech is insane. If you explore the compiler tech side of things, like you start trying to make your own compilers, that's like a whole other world. At least from the research that I've done, that's like a whole other world. It's like you've got on one, how do I even say this? It's like different levels, right? On You have a lot of this work that's done by compiler devs, and on top of that work, you've got the people that are using the compiler itself who are doing their various types of work, and on top of that, you've got other systems that are being built. But compiler dev is it's crazy. Anyways, okay, enough glazing compiler tech. Where was I in this? Project build system. Okay, course prerequisites in a university, or scheduling a sequence of jobs. All right. Then, minimum spanning tree. How can I connect all nodes with the minimum possible total edge weight? What it is, an MST is a subset of edges of a connected, undirected graph that connects all the vertices together without any cycles, and with the minimum possible total edge weight. Use case, designing a telecommunications network to connect multiple cities with the minimum amount of cable, or designing a water pipe network. Common algorithms, Prim's algorithm and Kruskal's algorithm. By understanding these core concepts, you'll be in a great position to read the petgraph documentation and see how its data structures and functions map directly onto this theory. I'm going to keep this open. I'm going to keep this conversation open because I want to export this later on and have this be one of the knowledge base things in my personal website when I do, whenever I do build the website. I want to have this present there. Okay, I'm also looking at the information that Gemini Web had given me, which I decided not to read and instead ask Gemini CLI. And it is similar information. Yeah, yeah, it is similar information. Actually, very similar information, give or take like one or two things. And those one or two things, give or take, they're not different. They're just lacking. So like in one of these, I think the Gemini CLI version gave me slightly more information than what the Gemini web web version had given me. Um, okay, so this is the algo module. This module contains most of petgraph's algorithms to operate on graphs. Some very simple search algorithms like DFS or BFS are implemented in the visit module. Oh, that's interesting. Okay, so that's what visit is for. The algo module contains multiple submodules, each implementing a specific algorithm or set of algorithms. Some functions, like connected components, are implemented directly in this module. It is a goal to gradually migrate the algorithms to be based on graph traits so that they are generally applicable. For now, some of these still require the graph type. Backup. It is a goal to gradually migrate the algorithms to be based on graph traits so that they're generally applicable. So like you implement the traits or you specify um, you derive these traits for a specific, like that's what I'm getting from this, right? Like how they would be approaching it. Maybe they would create like macros to set up the entire implementation, and then you would have like a derivable trait that you could you could specify when you're creating your struct. I mean, I guess I'll find out whenever they do implement that. For now, there's a bunch of these, um, and there's a lot. Holy shit, there's a lot. There's a there's a bunch for me to explore here. So there's a lot that I can learn. Um, yeah, dude. Okay, so now where do we go from here? I think the first thing that I should do is actually create a graph. Okay, so I guess let's do that. So the way to do that is mentioned here. So I'm just gonna set that up. There's a from elements thing. I think it's because, okay, this finds the shortest path from, okay, this is already doing the traversal thing. Hell yeah. Okay. And then get the minimum spanning tree of the graph as a new graph, and check that one, what? And that check that one edge was trimmed. Okay. All right. Print the tree to graphviz. This is what I'm looking for. And for that we need config. Config is from uh, dot graph. Okay. Well, the words. Config is from this. It's from the dot module, dot and config. So what all do I need here? For now I just want to define this thing. So for me it is ungraph or undirected graph, and I'm not doing any traversal. I don't know if I need from elements. Um, no, from elements is being used elsewhere. For now, just to keep it simple, we'll do this. And so let's do let G equals ungraph. And then we use this, the turbofish thing. I still need to read up on this, like exactly what is going on with this operator. Okay, from edges. What does from edges take? Oh God, it takes like 4 different generics. No, hold up. Wait, what is this? What is this signature? Um, oh, there it is. Now we have proper. Okay. From edges, it has to take an iterator. The type that you pass in has to be an iterator. So does array count as an iterator? Or does it have to be a vector? Yo, I clutched our group work in like 5 minutes and passed it. Last possible minute. OMG, I breathe now. Hell yeah. How's the graph stuff? It has been educational. It has been very informative. I've gotten to learn a lot about the different types of graphs and the different methods of traversing those graphs. And now I need to sit down and think of, um, I think I need to talk to Gemini about this to get some ideas for various very simple graphs that I can implement just to learn my way around graphs and get comfortable with graphs. For now, I'm trying to use the petgraph API to create a graph and then print out the dot graph syntax version of it. Now this requires an into iterator, right? Let's create a function, sum underscore func o1. This takes in t, which requires an into iterator. We don't need to be specific about the type. And then this takes in t, and we are good. Okay. Then here we will define an array and say this. Now let's see if I can do. Okay, yeah, that's why I can pass in into iterator. Is there also, there might also be an iter, right? Then yes, there is. So I can just pass in this. In an array, are we able to have tuples? Because I believe we can. This is probably going to throw an error, I think. If I, yeah, there's the error. They all have to have the same type. That being said, this works just fine. This is not an issue. So we can define what I'm assuming is a cyclic graph, and 0 goes to 1, 1 goes to 2, 2 goes to 3, and then 3 goes back to 0. So this is our edges. Okay, so then we define ungraph I32. And this, I need to understand this. I need to understand the type, the generic types that are being accepted here. Then from edges, and the edges that we specify here, the edges are basically anything that implements into iterator. That is interesting. So we can then pass in, give me a second. Okay. Yeah, that is interesting. So we can then pass in we can then pass in an array. We can pass in a vector. We can pass in any collection that implements into iterator, because the generic here literally says it should just implement into iterator. Man, I'm so glad that I learned how to do generic stuff. And I'm so glad that we explored the iterator and in fact are still exploring the whole iterator thing. Um, Holy shit, dude, there's so much to explore in iterators. Here, I thought it would be like a really simple topic, but there's just so much that I didn't know. Stuff like even blanket implementations that I just didn't know about. And yeah, dude, it's holy shit. I'm getting to learn. I'm getting to learn so much because I'm digging in into all of this information. We are still. Hold on. Let's go back to that conversation. Where is it? I think it's here. I think this is the one. Yeah, we are still here in iterators. I don't remember if it's going to ask us to, with this exercise, will give you a hands-on field on how to chain iterator methods and use closures to process collections efficiently. Yeah, dude. Holy shit. I am glad that I looked into all of this as much as I did, because I don't think I would have known that, oh, into iterator is implemented. There is another thing I need to look into. Um, Let me get back to this and then come over here. So what I need to look into here is what was I going to look into? Hold on. As iterator. Yeah. As into iterator. So edges dot into iterator, and then in brackets it says as into iterator. I need to understand what this as thing means, because we have a couple more. And then down there, there's use. These usually mean that we haven't added these use statements. And so if I hit enter now, it's going to add the use statement up there. You can see at the top it added that. Let's undo that. Um, so the use thing usually means that we don't have it added and it's going to add it. But I need to look at the as thing. What does it mean for it to be as into iterator? Why was I forgot why I was looking at this. Okay. Anyways, so this is our graph. This requires an iterator. So this requires an into iterator, something it can iterate over. So we're gonna pass this in. Actually, I don't think it requires you to move, does it? It requires, wait, it requires you to move? Because if we look, holy shit, look at this. Look at this. This is insane. This is crazy. Okay. Anyways, uh, from edges. Okay. Okay. Ty is edge type. Ix is index type. These are bounds from impl. Okay. N default. What is this thing? What is this line? I need to pass this entire definition into this entire like function signature into Gemini and get Gemini to explain it to me, because there's a whole lot of generic parameters and trait bounds going on here. I don't think any of them are, well, okay, hold on. Um, impl graph, I'm guessing from edges is a function a function implemented on graph, though um I'm calling it from this kind of thing. Hold on. I'm calling it from this. What exactly is this? Let's do this and then ungraph and I32 and this. What is this? I need to hold on just a minute. Okay. So, where was I? Yeah, I need to look into the what was it called? Turbo fish? Is that what it was called? I don't remember. Hold on. Because I forgot what it does. Turbofish, a parsing algorithm which mixes parsing and symbol lookup. Okay, combined with angular brackets for generics, this looks like a fish. Okay. As such, the syntax is colloquially referred to as turbofish. Examples, hold on, turbofish. Okay, paths with generic parameters in expressions must prefix the opening brackets with, oh God, wait, paths with parameters in expressions. Paths with generic parameters in expressions must prefix the opening brackets with um, double colon. Combined with angular brackets for generics, this looks like a fish. As such, this syntax is colloquially referred to as, yeah, okay. I'm still confused about I'm still confused about this. Okay, so and so prefix is required to disambiguate generic paths with multiple comparisons in a comma separate list. See the bastion of the turbofish for an example where not having the prefix would be ambiguous. I need to talk to Gemini about this. Hold on. I think I'll get a better understanding of this. Hey, I'm learning Rust and I'm super confused about how the turbo fish operator is meant to be used. I don't know if that's considered an operator. Is it? Hold on. Oh, how the turbofish syntax is meant to be used. Oh, how the turbofish syntax works and is meant to be used. Okay, welcome to the club. Okay, awesome. Thank you for that. Welcome to the club. The turbofish is one of those rustisms. Rustisms. What? Okay, the turbofish is one of those rustisms that looks bizarre at first, but eventually becomes a reliable tool in your kit. It's essentially a way for you to tell the compiler exactly which type you're talking about when it can't figure it out on its own. All right? Think of it as a nudge for the type inference system. What does it look like? The syntax is so and so. Okay, it looks like a little fish swimming to the left. It looks like a little fish swimming to the left. Okay. The two colons are the bubbles and the angle brackets are the fish. All right. Okay. Cool. Technically, it's used to provide explicit type arguments. Technically, it's used to provide explicit. Where was I? Uh, uh, words. Explicit type arguments to a generic function, method, or struct. All right. Oh, function, method, or struct. So in this case, what are we exactly like? So this is implemented back up. What did I just Oh God. Okay, back up, back up. Right, so we did edges, and then we read this. So this is graph impl graph. So this is, I'm assuming, I'm just going to take a guess here. I'm still new to trying to decode like these entire signatures and all. I'm going to take a guess that this is a function called edges, which is being implemented on the graph type, on the graph struct. If I'm right about that, is it a graph struct or a graph trait? I think it's a graph struct. I think so. Hold on. Um, what does this return? This returns edges. This returns edges. Oh, you know what? Wait, why is this edges different? Oh, it's supposed to be from edges. So from underscore edges. This takes in an iterable. We can remove all of this. This is supposed to take edges, which here we should be getting an error because the thing has been moved already, right? Uh, Back up. How are we not getting an error here? Oh, is it because it's copy? Maybe because it's copy. No, hold on. This is definitely not taking a reference, right? This is not taking a reference. We pass in, though here we seem to be passing in a reference, which I'm assuming is a slice. What would this count as? Let's do sum equals this and this. Does that work? What exactly is this? This is a slice, isn't it? So you have a slice and then oh God, I hit my keyboard. Okay. You have a slice and then you have the array. I need to go back and look at the basics because I've forgotten what the difference is between um, I've forgotten what the difference is between each of each of these and what each of them does. I know that like you can take a slice out of an array to read like a portion of the array, but like I need to get a better understanding of what each of them is. And I also need to understand this, like how are we able to pass this in? Let me try something here. Okay, let's wait. Instead, let's make this a vec and see what happens. There's the error. Now it has been moved, and that's why we are getting an error now. Use of moved value edges. Right. Okay. All right. But then would I be able to pass in this? If it's just reading the edges, would I be able to That's interesting. That is interesting. That's yet another thing I need to explore. Give me a second here. Wait, because um okay. You know what? Okay, this person popped up on my thing. I think we'll go to this person's and they get up and leave just as I said that. Amazing. Awesome. Give me a second here. Oh God, why all this slowdown, dude? Okay, this is interesting. So somebody is doing something. Okay, and then there's something here. Okay, right. I think we'll go to. Wait a minute. Okay, you know what? I'm gonna I'm gonna take us over to an artist's stream. Their name is That's Creative. Their name is Arth Vader. First, let me set up the raid and see. First, let me set up the raid and see if the raid even goes through. This person has the Godot tag, um, and they are doing some. They're doing what looks like pixel art right now, and yeah, their thing even says bots and pixel arts. No mic. Their tags are Godot, pixel art, English dev, and JavaScript. So they are currently, I think, animating something in pixel art. But yeah, that's gonna be it for today's stream. We're gonna head over to this person's stream. Drawn, thank you very much for stopping by and chatting and hanging out a bunch. I appreciate it. Anyone else who might have been lurking in the chat, thanks for hanging out. Um, we made some progress here. I'm definitely going to be exploring the concept of graphs a little more, and I'll play around with this a bunch because I'm really interested in this concept and like what you can do with graphs. And I wanna explore this a lot more. Let me first try and understand the turbo fish thing as well, completely before I move further, and then I have to do some research on that whole thing of like being able to pass in, you know, um, being able to pass in a reference where it's not asking for a reference and like what's going on there. So yeah, okay. That's gonna be it for today's stream. I hope you guys have a nice day, and I'll see you all next time. Peace.